Okay. So in fact, we do call that top angle there the vertex angle, right? And then the two angles that are touching the base or adjacent to the base, we call those the base angles. They don't have to be on the bottom, right? Just like the base does not have to be on the bottom. It's just whatever the third non-congruent side of that isosceles triangle, we call that the base. Or the side opposite the vertex angle there, okay? And the vertex angle has the legs as its sides, right? So just a little refresher there. All right, we can turn the page. All right, so explain one here. A theorem, isosceles triangle theorem. If two sides of a triangle are congruent, then the two angles opposite the sides are also congruent, right? This is also sometimes called the base angles theorem. Makes sense, right? If two sides are congruent, then those angles opposite those two sides should also be congruent. So if we go back and look here real quick, right? The legs are the congruent sides, and so these base angles opposite the legs, right? Opposite this leg is that base angle, opposite this leg is that base angle. They will also be congruent, right? So that's going to be true in general there. All right. We can actually prove this to be so. So if you look over here real quick, okay, on page 329 at the top, all right, you will see that we've got, man, I don't know where I put that red pen. You can see that we've got a proof to prove that given that AB and AC are congruent, that angle B and angle C, the base angles, will be congruent. All right, and we'll do that here real quick. So BA is congruent to CA, right? We're given that. Angle A is congruent to angle A by the reflexive property, right? Something is congruent to itself, reflexive property. Okay. Really strangely here, we're going to say that CA is congruent to BA by the symmetric property. Okay, it's kind of silly. Like, where did this come from? Well, if we said the BA was congruent to CA, then certainly CA is congruent to BA, right? So it's just like the reverse order there. But if you look, we just proved a pair of sides congruent, a pair of angles congruent, and a pair of sides congruent. So the triangle BAC is congruent to triangle CAB. I know it seems silly. It's like, Mr. Moore, that is the exact same triangle. And you're right, it is. Okay? But we're proving it congruent by side, angle, side. Okay? Triangle BAC is congruent to triangle CAB. So corresponding parts of congruent triangles are also congruent. In other words, B here is in the same position as C here. So angle B is congruent to angle C by CPCTC. Okay? So we can use that CPCTC to prove that base angles in an isosceles triangle are congruent. Okay? So that's the idea of that. And then by a similar argument, we can also prove the converse. If we have base angles that are congruent, then we know that the opposite sides will also be congruent, just like that. Okay? So we'll take a look at that here. Let's take a look at that proof here, too. All right, so now we're just going to go in reverse. Oh, of course I don't have those notes down there. Okay, now we'll just go in reverse here. So we've got angle ABC is congruent to angle ACB. Okay, that was given. Okay, and then we have two things are congruent by the reflexive property of congruence. Well, it's the same thing. It's angle A is congruent to angle A there. Okay, or actually, I'm sorry, we're not going to use angle A. Although that would be true, that's not going to be helpful in this case. I apologize. It's segment BC is congruent to segment BC. Okay, my apologies there. We're going to use BC congruent to BC. Okay, and then since angle ABC is congruent to angle ACB, we'll flip the order around there by the symmetric property, and so angle ACB is congruent to angle ABC. Okay, so then triangle ABC is congruent to triangle ACB. Okay, we're just flipping the order around there. And that's by, well, if you look at it, we have an angle, a side, and an angle there. And so this is congruent by angle, side, angle. And then we can say that AB is congruent to AC, because again, you can see here, AB, that side, is in the same position as AC. And so that's true by CP, CT, C. Okay. This proof is so like basic or simple that it's actually complicated, I think. We're talking about proving two triangles congruent when they're the exact same triangle, just in a different order. And by proving it as the same triangle but using different order of letters, we're then able to match up that AB then has to be congruent to AC by starting with that. And so that's how we get it using CP/CTC. Okay? But long story short, base angles in an isosceles triangle are congruent, and they're opposite the congruent sides there. Okay? And then the last little bit here, and we're not going to worry about proving this is true because it's so silly. But if a triangle is equilateral, it's equiangular. So like things that we've assumed to be true, we now know to be true. It's a theorem. Okay? Likewise, if a triangle is equiangular, then it's equilateral. Okay? So boom, we can, be good to go with that. All right? So that's the idea there. And of course, then we can use these relationships to help us. All right? So for example, if we go to the next page here, okay, we will come across a, an error in the book here. We can see here that this is, what kind of triangle will we name this triangle to be? Based on the fact that angle B and angle C are congruent, what would we name that triangle to be? By its sides. Isosceles. It's got to be isosceles, right? If angle B and angle C are congruent alone, then that means AB will be congruent to AC. Okay? And here's the error in the book. I think they mislabeled things here because we don't have a way to relate these two sides, okay, given this information here. So let's go ahead and just say that this is 4x plus 7 right there, and then you guys, we can solve it from here for x by setting them equal to each other, getting x and then plugging back in to find the actual length and stuff like that. So I won't do that. Likewise here with letter B, okay. Let's say we want to find the measure of angle T here. In order to find angle T, we need to find what? X, right? All right, so how can we relate the 3x and the x in this triangle here? What could we do? We only have two angles. We know that if we had the three angles, it would add up to 180 degrees. Right, so Madison?
You know that R and S have to be equal.
Right, R and S have to be equal. They're the base angles, right? R is opposite this side, which is congruent to this side, which is opposite S. So this is also going to be x degrees. And so we can set it up as 3x plus x equals 180. And then solve from there. We get 5x equals 180 degrees. And so we get x equals, x equals 36. Okay? But, oops, sorry, I'm off the screen there. But of course, we're not done with x being 36. We're going to plug that back in. So measure of angle T is equal to 3 times that 36. So is that 108? I believe there. 3 times 30 is 90. Yep. Okay. So again, just using the properties of the isosceles triangle there. Stuff like that. Okay. Okay. And then if you turn the page once more here, just to kind of get an idea, you can see that, okay, here again, it's another isosceles triangle. If we want to find the measure of angle P, P is going to be congruent to what other angle in this triangle here? Q, right? They're base angles. Okay, so here you can see the base is not the bottom, but this would also be 3x plus 3. And you could solve by adding them all up, setting them equal to 180, solving for x and stuff like that. Okay, but we're not going to worry about that. We're going to keep moving here on to next section. Okay, triangle inequalities. Okay, 7.3. Okay. Okay, two other additional relationships here. Okay, the first is called the triangle. So this is the triangle inequality theorem. Okay, and so this one is crucial here too. The sum of any two side lengths of a triangle is greater than the third side length. Okay, the sum of any two side lengths of a triangle must be greater than the third side length. Okay? So in order for a triangle to exist, the sum of any two side lengths must be greater than the third side, okay, that you don't include. So in other words, AB plus BC must be greater than AC, BC plus AC must be greater than AB, and AC plus AB must be greater than BC. So the way that we kind of use that is an example like letter A here. Okay, use the triangle inequality theorem to tell whether a triangle can have sides with given lengths. Explain. So if you have a triangle that's got a side lengths of 4, 8, and 10, can you add any of the two sides together? Will it be then greater than the third side? So you can see here, is 4 plus 8 greater than 10? Yes. Is 4 plus 10 greater than 8? Yes. Is 8 plus 10 greater than 4? Yes. So this triangle can exist. But if you look at a problem like B, 7, 9, 18, can this triangle exist? Well, 7 plus 9 is what? 7 plus 9 is 16. Is 16 greater than that third side? No. So this triangle cannot exist. And we're on page 343 there. Okay, doesn't matter about the other two, doesn't matter. If any two sides don't add up to be greater than that third side, it's not a triangle. Okay? So then if we had an isosceles triangle that had side lengths 5, 5, and 10, would that exist? Can we have an isosceles triangle that has side lengths of 5, 5, and 10? 5 plus 5 is 10. Is 10 greater than 10? No. So that triangle wouldn't exist. Okay? Same idea here. You can take a look, right? So like for number 6, for example, 12 plus 4 is 16. That's not greater than 17, so this triangle would not exist. And then 24 and 8, 32. That's greater than 30. And then 8 and 30 is greater than 24. And then 24 and 30 is greater than 8. Okay, so this triangle would exist there. Okay? So that's that triangle inequality theorem. Any two sides have to add up to be greater than the third side. Okay? And then on the next page over there, page 345, there is the thing we talked about in the warm-up. If two sides of a triangle are not congruent, then the larger angle is opposite the longer side. Okay? So here, for example, since AC is longer than BC, that means the measure of angle B is greater than the measure of angle A. Okay? The largest side is opposite the largest angle, the smallest side is opposite the smallest angle, and the middle-sized side is opposite the middle-sized angle. Okay? And that's all I wanted to show you guys there for that. Questions on any of that? Okay. So, you have some options today as far as what review you would like to do. Okay? There will be no homework tonight, but I will give you some time, the rest of the time here, to work on more proofs if you want to. I also have some, if you want to practice some of these problems we just talked about, okay, that's fine too.